Professor Clements with you as we consider again Chapter 19 in the OpenStax College Physics book. I'm working with my reading guide on this. We're in Sections 5, 6, and 7 of Chapter 19, talking about capacitors and dielectrics, capacitors in series and parallel, and energy stored in capacitors. So we're dealing with one of the three big elements of electric circuits, the capacitor. In the future, we'll talk about resistors, and we'll talk about briefly inductors, although we won't pay as much attention to them as capacitors and resistors in circuits. A capacitor, simple drawing would be two parallel plates. If we connect them to a battery, this plus pole of the battery will remove electrons from this plate, and it will deliver electrons to the plate on the right. Of course, to push electrons onto here and create a surplus of electrons, that's going to take work, and that delivers energy to the capacitor. So a capacitor can be said to store charge or store energy. And as the electrons are moved to this side, one electron going off to the right, there'll be one electron pulled off from the left. So we end up with the same magnitude of charge on both plates, a plus Q, a minus Q, and we use the symbol capital Q by convention here. Instead of the small q we used when we did Coulomb's law calculation. Capacitors may also be more of a spiral shape for the conductors. But what's in common, there is an insulator of some sort. Air is an insulator to a certain degree between the plates here, or in the future we'll talk about using special material for the insulator on the capacitor. There's a relationship between how much charge is on the plates of the capacitor and the potential difference of the capacitor. And we can, if I get into so now into slide mode here. If I again talk about the plates of the capacitor, there's a certain voltage between the two plates based on how much charge is on the plates. And the situation we have is that the capacitors can be built in a variety of shapes. You see them here, and there are different labelings or color codes. We're not going to worry about those, but let's move on to some more important things, the physics of the capacitor. So if we have more charge on the plates of the capacitor, then the electric field is going to be larger. There can be more electric field lines here. The larger value for the electric field. Electric field is related to potential. If you recall, electric field can be calculated with the potential difference divided by the distance between the two locations. We're working on a straight line in a uniform electric field. Or we could calculate the potential by multiplying the electric field by the distance along this uniform field line. So we have a relationship between Q and V. If Q is bigger, V is bigger. This is a proportionality. The constant of proportionality is this new symbol, capital C, and this is not coulombs. This means the capacitance of the device. And the units of this are in farads, in honor of Michael Faraday, an 1800s, self-taught, this person who studied electricity. The capacitance measured in the standard metric unit of the farads. It turns out we can calculate the capacitance of a parallel plate capacitor with this formula. Epsilon naught is a constant, the permeativity of free space. Look that up in whatever book you have handy. I think it's 8.85 times 10 to the minus 12. A is the area of one plate in square meters, and D is the distance between the two plates in meters. So you notice this is a calculation based on geometry. The capacitance depends on the geometry of the capacitor. For the parallel plates, it's a case of the area and the distance between the two plates that make a difference. A good exercise is to calculate the area and then the length of one side if the capacitance is 1 farad, and you'll be a little bit surprised, and let's choose 1 millimeter for the distance between the two plates. You'll be a little bit surprised at how large this parallel plate capacitor has to be. And there's a solution for this problem, but let's continue. So we have the capacitor, parallel plates. The capacitance value is a constant proportionality between charge and potential difference on the plates. So we're going to go a little bit further here and discuss our calculations involved with the capacitor. If I can advance my slide. So perhaps you did that calculation for the size of a parallel plate capacitor at something like 10.6 kilometers for one side of the plate. If we have 1 farad and the distance between the plates is 1 millimeter. Well, that's too big for a computer that holds a capacitor, or your cell phone that has capacitors in it. So there's a way of making the capacitance larger. One of those ways is to put something called dielectric in between the two plates. Dielectric is an insulator. It's an insulator that polarizes in the presence of an electric field. So the electric field here is Q minus Q. The electric field would be running across from left to right in this transparency, this slide. That causes the molecules of the dielectric to polarize. The negative part of the molecule does not separate from the molecule, but it goes to one side to be closer to the plus plate. The electric field of the dielectric points to the left. The electric field of the plates points to the right. And the net electric field is now smaller between the two plates. Again, the electric vector adds together. We have an electric field to the right from the plus Q minus Q arrangement. We have electric field to the left from each of the molecules here. And the net electric field is then smaller. Well, the potential is something related to how much electric field we have. Potential is electric field net times the distance across here. So we end up with less potential difference across the capacitor. If we have the same amount of charge, we're going to have a smaller net voltage. To get this same amount of charge as we had without the dielectric, it turns out the capacitance value changes. The capacitance value is calculated with geometry, and then also the effect of this dielectric increases the capacitance. Different materials have different dielectric constants depending on how well they somewhat partially neutralize the original electric field. But we have a net electric field that's a little bit smaller. We still have this Q equal CV. So on the calculation with the, I don't have it here, but on the calculation with the geometry effect, there's a kappa, dielectric constant factor in here. So kappa times epsilon naught times A divided by D, and you can look up the value of kappa in your textbook. All right, let's move to now combinations of capacitors. The first one we'll consider will be the capacitors hooked up in series to a battery. Series means end to end. Parallel will be side to side. So we have the plus terminal of one capacitor, we have the negative terminal, and then the negative terminal of this capacitor is hooked up to the plus terminal of this capacitor, negative to plus, and then negative to the negative of the battery. As we would analyze this circuit, the battery has a certain potential difference across the poles here, maybe 12 volts if it's a car battery, and there's going to be 12 volts of potential difference across these three capacitors. Those individual voltages add up. Some of the voltage is across the first capacitor, some portion of the voltage is across the second, some portion of the voltage is across the third capacitor. The V's, V1, V2, and V3 add up to the total V of the battery. An individual voltage can be calculated by Q over C. I'm just rearranging the fundamental capacitor equation. Q equals CV is the fundamental relationship. So let's solve for V. We get Q over C. It turns out on the series capacitor, for the analysis that this course goes into, the charge is the same on each capacitor. You can see that's labeled in the diagram here. The Q's are all equal. Well, so just imagine Q over C here, Q1 over C1 here, Q2 over C2, Q2 over C3. The Q's are all the same. So consequently, we can cancel off the Q's, and we're left with just the C's, just the capacitance. And we can calculate the series equivalent capacitor. If I wanted to take out these three and replace with just one capacitance to get the same electrical effect, the same value of capacitance, this is the way we would calculate it. It is a reciprocal calculation. 1 divided by C sub s equals 1 over C1 plus 1 over C2 plus 1 over C3, and there'll be example problems on how to calculate that. If we have the capacitors hooked up in parallel, side to side, now the plus plates of the capacitor are all hooked together. These are wires. The minus plates are hooked together. And in this situation, now the voltage is the same across each capacitor. Now, it doesn't matter which capacitor you pick. It's hooked up by a wire to the plus terminal of the battery on the top, hooked up by a wire to the negative terminal of the battery on the left. If this is a 12-volt battery, each of these three capacitors will have 12 volts across the capacitance. There's a total charge that's stored in this system. That's the sum, Q1 plus Q2 plus Q3. I can replace each Q with C times V. The parallel equivalent, C here, times the voltage across that parallel equivalent, C1 times V1, C2 times V2, C3 times V3. But V1 equals V2 equals V3 equals the V that I put over here. All those V's cancel off. Tried that yourself. Didn't have room for it on the slide. We end up in calculating the parallel equivalent. There should be a sub P on here. The parallel equivalent capacitance is C1 plus C2 plus C3. So we calculate series equivalent capacitance with the reciprocal formula. For the parallel, it's easier. We just add the capacitors' values together. In analyzing a circuit that's a combination of series and parallel, you go step by step. I cannot apply the parallel formula here with C1 and C3. They're not strictly just in parallel with each other. We've got this C2. So the first step would be to do the series calculation for the 1 microfarad and 5 microfarads. Then the two values here are in parallel with each other, and they can just be added together. And we'll have some example problems of that. Here is a device with some capacitors in it. You can see the little orange blobs here. You can see some down here. You can see some, I'm not sure if these are capacitors or not, but they can be made small enough to fit inside your cell phone or your calculator. And they store charge, they store energy, they help the circuit behave the way the electrical engineer designed it to behave. Defibrillators have a battery inside that charges up a capacitor, delivers energy, accumulates energy, enough energy to give a shock to a person to restore their normal heartbeat. What would you do here in simplifying this circuit if I want to find a single equivalent capacitance? Would you do a parallel calculation first or a series calculation? You cannot do a series calculation. The 10 is not in series with the 0.3, not in a simple series. You have to do this parallel calculation first. So you get 12.5 as the equivalent parallel capacitance, and then you would do the calculation with the 0.3 in series with it. Here, again, you have to do the series first, get an equivalent capacitance here, and then do the parallel calculation. For this one, a little bit more complicated, but you'd go step by step. So here is a series arrangement. We do that first. Then we could do this parallel calculation. We could do the parallel calculation here, the 0.75 and the 15. Then we could do a series calculation here. And then we could do this net parallel and this net capacitance over here and calculate. But you'll just have to kind of gain experience with that to recognize what is a series arrangement, what is a parallel arrangement, and which you can perform first as you do calculations. So those are the key principles here with capacitors. I could comment a little bit on the energy of a capacitor. The energy is 0.5 times the capacitance value times the square of the voltage across the capacitor. So that would wrap up our discussion of Chapter 19 with the topic of capacitors. Keep reading. You should be working your own sample problems, reviewing examples in the textbook.